Welcome back to the Explainer. Okay, let's dive right into this. Today, we're cracking open the blueprints on drone engineering, specifically focusing on Week 2's core concepts, the unsung hero of every single flight. Yep, we're talking about the frame and the materials that make the whole thing possible.
I mean, think about it for a second. You've got high-speed motors, heavy lithium batteries, ultra-sensitive flight controllers, and they're all vibrating intensely while fighting gravity. So what actually keeps all these fancy, expensive components from just shaking apart and dropping right out of the sky?
Well, the answer is the drone frame. It's basically the structural base, or the skeleton, that holds the whole shebang together. Without this incredibly solid foundation, your high-tech motors and massive batteries are honestly pretty useless. They'd just be a pile of loose parts on your workbench.
Here's our flight plan for today. We'll cover 1. The skeleton of the drone. 2. Choosing a frame design. 3. Material analysis. 4. Balancing weight and load. And finally, 5. Drone frame manufacturing methods.
Starting off with Section 1, the skeleton of the drone, the foundation of flight.
So this frame supports all the vital stuff, right? The motors, the flight controller, the battery, the propellers. A drone's overall performance, its stability when the wind kicks up, its durability if you happen to crash, it absolutely all depends on how well this skeleton supports those vital organs. If the skeleton flexes even a tiny bit when it really shouldn't, the flight controller gets totally confused and boom, the drone crashes. It's a super direct cause and effect relationship.
Moving on to Section 2, choosing a frame design, the shapes of flight.
Now, what's really interesting here is how just simple geometry completely changes how a drone behaves in the air. But before you even pick a shape, you have to know your mission. Are you building a rig for racing and freestyle where it's going to be zipping through a super tight obstacle course at breakneck speeds? Or are you needing it to carry large payloads, like heavy 4K cameras or agricultural sensors? Or maybe you're just putting together something basic for research and education. The point is, different missions absolutely require completely different frames.
And naturally, every design comes with trade-offs. Take the X-frame. That's your classic racing design. Because the motors are equidistant from the center, you get this perfect symmetry, which translates to just incredible agility and perfectly balanced control. On the flip side, the H-frame has a much wider body. Now, it sacrifices some aerodynamics and definitely adds some drag, but in return, it gives you that much-needed internal real estate to mount those heavy cameras and sensors. And finally, we've got the plus frame. It features arms in a cross shape, which actually simplifies the whole control algorithm. That makes it awesome for educational purposes, but, fair warning, it gives up a whole lot of maneuverability compared to that snappy X-frame.
Okay, Section 3, material analysis for drones, the building blocks. Engineering is really all about managing tension and making compromises. On one hand, you've got carbon fiber. It's the go-to for high-performance drones because of its absolute knockout strength-to-weight ratio. It's incredibly rigid, super lightweight, and it resists vibration like a champ. But it's going to cost you. On the other hand, you have plastic, or ABS. It's super cheap, totally beginner-friendly, and it's actually flexible enough to bounce back from minor crashes. The catch? It's much heavier and way less rigid, which definitely degrades your overall flight performance.
But hey, here's a really surprising, vital fact about carbon fiber. It is actually brittle when subjected to impact. Yeah, despite its incredible strength and rigidity, carbon fiber has this one crucial weakness. If you crash it hard into a tree at 50 miles an hour, it doesn't just bend like plastic would. No, it straight up shatters or snaps. So as you can see, even the absolute most premium materials out there have their own Achilles heel.
And then we have the industrial middle ground, which is aluminum frames. Aluminum is tough, it's strong, corrosion-resistant, and highly durable. Now yes, it's definitely heavier than carbon fiber, but engineers will purposely choose it for industrial-grade drones because in those cases they're prioritizing survival in really tough, gritty environments and ease of manufacturing rather than trying to shave off a few tiny grams of weight.
All right, Section 4, balancing weight and load, the physics check.
So the crucial point here is a concept called the weight-to-lift ratio, and a 1:2 ratio represents a really solid common benchmark. The golden rule in the sky is literally this. A drone should be as light as humanly possible while still safely lifting its required payload. If you just pack on too much weight, whether that's heavy plastics or massive, chunky cameras, without upgrading your motors to match, you completely ruin this ratio. And the result? You're looking at dangerously sluggish performance and just terribly low flight times. Not fun.
And right alongside that weight ratio is something we cannot ignore: the center of gravity. Having an optimized center of gravity is absolutely non-negotiable. I mean, you could build a gorgeous top-of-the-line X-frame out of premium carbon fiber, but if you slap a heavy battery hanging way off the back left corner, you've completely ruined the balance. Uneven weight distribution practically guarantees mid-air instability and severe control issues.
This means if your drone's specific mission is to carry cargo or sophisticated sensors, those payload distribution requirements honestly change everything. Adding external sensors physically forces engineers to reinforce the frame. It dictates that you simply must pick stronger, beefier motors. You really can't just tape a heavy camera to a basic frame and call it a day. It requires a holistic, ground-up redesign to prevent a totally catastrophic failure mid-flight.
Let's move to Section 5, Drone Frame Manufacturing Methods, the assembly line. So how do we actually build these things? Modern manufacturing always comes down to balancing cost versus flexibility. If you're mass-producing beginners' plastic toy drones, you're going to use injection molding. It allows for just massive production runs at a remarkably low cost per unit, but you have almost zero design flexibility once that expensive metal mold is cut. Now, if you need real industrial strength, you turn to CNC machining. It carves out incredibly precise, rock-solid parts from carbon fiber or aluminum, but it's expensive and it's slow. And then, of course, there's 3D printing, which has become hugely popular for anything custom, experimental, or educational.
Let's actually compare these two cutting-edge methods directly. CNC machining gives you that time-consuming, absolute exactness. It's exactly how you get those flawless, high-strength parts for professional, top-tier drones. But 3D printing, that offers just incredible prototyping freedom. It gives engineers massive design flexibility at a much, much lower cost for small runs. It literally allows a team to dream up some wild, out-of-the-box new frame design in the morning, print the thing out over lunch, and be test flying it in the afternoon. It's a total game changer.
And I think that brilliantly illustrates the whole engineering journey we've mapped out today. We've seen exactly how geometric frame shapes dictated drones' agility, how materials like carbon fiber balance extreme strength with that surprising brittleness, and how strictly managing the center of gravity keeps the whole system soaring safely. But look, with technologies like 3D printing evolving literally every single day and wiping away all those old manufacturing limits, what radical new skeleton are you going to design for the skies of tomorrow? Thanks so much for joining me on this explainer, and hey, keep exploring.